Welcome back to the deep dive. Today, we are taking on a problem of truly, well, astronomical scale.
It really is.
We're talking about cloud computing data centers. I want you to just try and picture this landscape for a second.
It's almost impossible to fully grasp.
You have thousands upon thousands of different applications running across this huge, heterogeneous fleet of machines,
And when we say thousands, we mean tens of thousands of them.
all serving live global traffic, 24 hours a day. In an environment like that, efficiency is everything. It's directly tied to operational cost.
Every single instruction matters.
Exactly. If you can find and get rid of inefficiencies that save even a tiny fraction of a percent of computation fleet-wide, that translates into, well, huge cost savings.
We're talking hundreds of millions of dollars.
But here's the hook, and this is the core constraint that really drives the entire design we're going to be talking about today. How do you continuously monitor the performance of all of these processes and the kernel modules and all the underlying infrastructure without slowing down the very things you are trying to measure?
Right, the observer effect.
Because if your monitoring tool adds any significant latency or resource consumption, the application owners are just going to turn it off.
And then it's useless. You can't capture that fleet-wide behavior.
It's a complete non-starter.
Precisely. And this challenge goes so far beyond the typical task of, debugging a single piece of slow code.
This isn't just one developer on their laptop.
Not at all. It's about achieving a reliable, continuous, fleet-wide understanding of efficiency, resource consumption, microarchitectural behavior. Really, the whole pulse of the data center.
So that's what we're doing today. We're diving into the sophisticated infrastructure Google created to solve this immense problem. It's a system known as Google-wide profiling, or GWP.
Right. And GWP, it acts as this crucial shortcut for you to be well informed about the operational health of this massive compute infrastructure.
A shortcut, I like that.
Our mission in this deep dive is to unpack its multi-component system architecture, its, frankly, groundbreaking non-intrusive data collection strategies. And this is the part I find most compelling. The surprising application of information theory and some really complex mathematics that they use to validate this sparse, noisy sample data and turn it into reliable, actionable certainty.
Okay, let's unpack this, because GWP makes a staggering promise.
It does.
Stable, accurate profiles delivered with truly negligible overhead. We are talking about a measured overhead across the entire computing fleet of less than 0.01%.
It seems impossible.
That number just seems impossibly low for the depth of data they claim to capture, and we are going to explore exactly how they engineered their way to that figure. So let's start by defining why the old ways just wouldn't work here. Why were traditional methods so completely insufficient for this kind of scale?
Well, most performance analysis tools, and you can think of older Unix tools like gprof or even modern commercial profilers, they're all designed for a different world.
The smaller world.
A much smaller world. They're built for isolating benchmarks or running these highly detailed traces or analyzing a single program execution in a very controlled environment.
But that whole model just collapses when you face the reality of a modern large-scale data center.
It completely falls apart.
These cloud applications are so dynamic, workloads fluctuate constantly based on global demand. They rely on distributed state, shared kernel resources.
And they often run across different machines in totally different data centers.
Right. You just can't press pause on live traffic. You can't tell Google Search or Gmail or Maps to hold on for a minute so you can attach an intrusive debugger or run a full tracing utility on one machine for an hour.
Exactly. That sheer scale is the first barrier. But the second, and I'd argue the architecturally defining constraint, is what you mentioned earlier, the overhead constraint.
This is the rule that shapes everything else.
It really is. Application owners who are running these critical latency-sensitive services have incredibly strict limits. They will not tolerate latency degradations of more than a few percent, if that.
So if a profiling tool is even perceived as intrusive, it's dead on arrival.
Immediately unusable. And you have to think about the aggregate cost. At Google scale, any unnecessary profiling overhead, even just 1%, translates into millions of dollars in wasted computation or hardware you have to buy to compensate.
So minimal observer distortion isn't just a nice-to-have goal.
It's an economic imperative. It's a hard requirement.
So, okay, that leads you to one place. The foundation of the solution had to be sampling-based.
It's the only way. It's the only way to manage that resource consumption and bring the fleet-wide overhead down to that near-zero level you talked about.
That 0.01%.
That's a target. And GWP is, conceptually, an evolution of some earlier ideas.
Yeah.
specifically something called the Digital Continuous Profiling Infrastructure, or DCPI, which was originally developed at Compaq and HP.
But GWP takes that concept and just scales it to the moon.
It vastly extends it, yeah. It's
Oh.
continuous profiling applied fleet-wide, sampling simultaneously across thousands of heterogeneous machines and multiple geographical data centers, and collecting all these diverse event types at once.
And this continuous collection at scale immediately introduces what has to be a gargantuan data volume challenge.
Oh, absolutely.
You're collecting detailed profiles from several thousand applications running on thousands of servers every single day.
The output is just immense. The compressed profile database, it grows by several gigabytes every single day.
And that's compressed.
That's compressed.
Yeah.
And we're not talking about a simple text file. This is complex, indexed, sparse data. Just managing the ingestion pipeline, ensuring that these tiny, sparse samples are statistically representative of the whole population.
And then making this massive data set accessible for analysis in something close to real time.
It becomes a huge engineering hurdle in and of itself.
But the payoff, I mean, the reason you solve these incredible scale and trust challenges is that the value proposition is enormous. GWP lets you see patterns that are completely invisible to a single application developer.
That's the whole point. It lets infrastructure owners ask these incredibly valuable, aggregated questions that impact large-scale resource allocation. It moves you beyond the classic, hey, which function is slow in my app?
Right. It's a bigger picture.
It's a much bigger picture. You're asking, what are the globally hottest processes or routines across the entire data center fleet?
Which would let you spot, say, a shared library that everyone uses that's secretly inefficient.
Exactly. Or which synchronization primitives or locks are the most contended globally. That could indicate a systemic issue with how you're managing threads.
And what about hardware performance?
A big one. What is the average cycles per instruction, or CPI, across specific hardware platforms? That's the cleanest metric you have for judging how efficiently a processor is actually executing instructions.
And you can get even higher level than that, right? More architectural questions.
For sure. Things like, how much resource utilization are we losing because of suboptimal job scheduling decisions? Or what's the current distribution of 32-bit versus 64-bit applications across the fleet? That can guide migration efforts.
Or even something like, are we consistently compiling our binaries with the latest, most efficient compiler versions everywhere?
Yes. All of these aggregated insights, they directly inform billion-dollar hardware and software infrastructure investment decisions.
Okay, so to handle this kind of scale, GWP had to be a whole infrastructure, not just a single tool.
Right. It's a full-on distributed system.
And if we look at the blueprint, it's made up of several core components. You have the collectors, the daemons on every machine, a centralized binary repository, the symbolizer, the profile database, which they call an OLA cube, and a web server interface.
Let's start with what you could call the operational heart of the system, the collector.
The brains of the operation.
You could say that. The collector is a highly distributed service, and it's designed from the ground up for robustness and high availability. It has to be, because it orchestrates the sampling across the entire fleet.
So walk us through its specific mechanism. I'm picturing it as like a sophisticated foreman dispatching tasks across a vast factory floor.
That's a real good analogy.
Yeah.
Periodically, and this process is just running continuously, the collector first retrieves an up-to-date list of all the currently active machines from a central machine database.
And that database has more than just names, I assume.
Critically, yes. It provides metadata like the machine names, their current status, and key hardware characteristics, CPU type, core count, that sort of thing.
Then what?
Then the collector applies its sampling algorithm and selects only a small randomized subset of those tens of thousands of machines for the next profiling run.
So it's not hitting every machine at once.
No, never. That's a key part of the overhead mitigation. Once that subset is selected, the collector remotely activates the profiling mechanism on just those machines and then retrieves the raw results.
And it's a dynamic process, you said. It doesn't just grab everything in one go.
That's right. It might gather hardware performance counters, HPMs, for just a few seconds. Then it might move on, either sequentially or concurrently, to profile for something like lock contention or memory allocation on that same machine. The whole thing only takes a few minutes per machine being profiled.
What happens if something goes wrong? I mean, these are live production machines. You have to have fail-safes.
They are absolutely paramount. The collector is constantly monitoring for error conditions like connection timeouts, or if a profile collection fails for some reason.
Okay.
If the failure rate for a specific profile type or a specific machine type hits a predefined threshold, the collector just immediately stops that type of profiling.
It backs off.
It backs off until the underlying infrastructure stabilizes. That minimizes any potential distortion on those critical applications.
Okay, so that's the collector. Next in the chain, we have the daemons. You describe them as these lightweight gatekeepers deployed on every single machine in the fleet. Why are these so necessary if the collector is doing all the orchestration? Why not just let the collector talk directly to the operating system profilers?
The necessity of the daemon really comes down to two things: permissions and control,
Security.
security and safety. Most application users, and even many system administrators, they just don't have the root access required to invoke whole machine kernel profiling systems directly.
And you wouldn't want them to.
You definitely wouldn't. So the daemons act as these trusted, privileged intermediaries running locally on every single machine. They control access, they enforce strict limits on the sampling rates.
So they prevent any single request from overwhelming the machine.
Exactly.
Yeah.
And they're also responsible for collecting synchronized system variables, things like process IDs, uptime, memory usage, that have to be accurately correlated with the profiles taken at that exact moment.
That makes perfect sense. The daemon is like a firewall, ensuring compliance and safety. Now, let's look at the actual inputs. GWP gathers two distinct categories of profiles.
Correct. The first category is the whole machine profiles. These are the most comprehensive. They capture all activity on the machine.
User apps, the kernel, background processes, everything.
Everything running. This data primarily comes from hardware performance monitoring, or HPM events. It uses sources like OProfile to gather data on CPU cycles, cache misses, retired instructions, and so on.
And that must be tricky with all the different hardware types.
It is. A crucial detail is that the system defines generic HPM events. This allows the data to be normalized, even with the heterogeneity across all the different processor architectures: Intel, AMD, custom designs.
Very clever. And the second category, the per-process profiles, seems more focused. It's about getting deeper stack trace granularity for specific applications.
Yes, these profiles are collected directly from applications using the Google Performance Tools library. And this library is, for all intents and purposes, linked against almost every major application running in the data center.
So it's built right in.
It's built right in. This library enables these process-wide mechanisms for stack trace attributed profiling. So you get detailed metrics like heap allocation, lock contention, wall time, and very fine-grained CPU time.
And how does the collector get that data?
It's pretty neat. The GWP collector uses the cluster-wide job management system to find out exactly where an application is running, and then it sends a request via the application's built-in HTTP server handler to just retrieve the profile data directly. This approach lets them capture the vast majority of running programs across the entire system.
All right, this brings us to what you called the secret sauce. The core technical innovation that makes that negligible overhead figure, that less than 0.01%, even remotely achievable.
It really is the heart of the whole system.
Two-dimensional sampling.
Two-dimensional sampling.
Okay.
And to understand why it's so necessary, let's first look at why sampling in only one dimension just fails. So let's say you tried to do continuous event profiling on every machine, all the time. Even if you set a low event rate, the total aggregate resource usage across the entire fleet would still be way too high. It would be economically prohibitive.
Right, that's a machine-only sampling failure. Too broad.
And conversely, what if you only sampled machines very infrequently? Say you profile a machine once a month.
The data would be stale and probably useless.
Exactly. The event profiles you collected might be so sparse that they don't capture any meaningful activity at all. So your drill-down analysis is worthless. That's an event-only sampling failure. Too sparse.
So GWP realized they had to tackle this problem in both dimensions at the same time to thread that needle between being non-intrusive and still getting rich data.
That's the key insight.
Okay, so the first dimension is the machine dimension. This is the spatial filter.
Right. Profiling only occurs on a small, randomized, statistically representative subset of all the machines in the fleet at any given moment.
So you're immediately limiting the total resource consumption fleet-wide to just that fraction of machines.
Exactly. And the second dimension is the event dimension. You can think of this as the temporal filter.
How often you look.
How often you look. Event-based sampling is used at the machine level. They're only sampling specific measurable events like, say, CPU cycles every few thousand cycles, or a cache miss once every million events. It's not constant, exhaustive monitoring.
And they choose a local sampling rate that's high enough to capture meaningful data quickly, but low enough that it doesn't distort the local performance.
That's the balance they have to strike.
It's an elegant combination.
Yeah.
You limit where you look, the machine's subset, and you limit how often you look, the event rate. It's the statistical trade-off that makes the massive scale possible.
And this dual sampling is then backed up by several other really critical overhead mitigation techniques.
Like what?
First, they are extremely conservative. They benchmark this event-based profiling overhead on standard applications, and they set the absolute maximum sampling rates based on those very conservative measurements.
So they can guarantee that the overhead is always less than a few percent locally, no matter what the workload is doing.
That's the goal.
Okay, now, let's talk about a fascinating trade-off in the design, something that really surprised me. The decision they made about call stacks.
Yeah.
To prevent what is probably the single biggest overhead associated with profiling stack unwinding, they actually do not collect whole call stacks for those high-volume, whole machine HPM profiles.
This is a huge but necessary sacrifice, and it just speaks to how strict that overhead constraint really is.
Can you explain what stack unwinding is for those who might not know?
Sure, stack unwinding is the process of walking the program's call stack to figure out the sequence of function calls that led to the current point of execution.
So function A called function B, which is called function C.
Exactly. But that process is complex. It often requires accessing memory, looking up symbol tables, and it can be incredibly costly in terms of CPU cycles, especially when you have to do it frequently or in kernel space.
So by just avoiding whole call stacks for the big fleet-wide HPM profiles, they eliminate a massive source of resource consumption.
A massive source. They reserve the costly collection of stack traces only for those per-process servo profiles we talked about.
And even then, I bet they do it less often.
Oh yeah, they collect them at much, much lower sampling frequencies.
That decision right there makes that less than 0.01% figure much more believable. They're basically offloading the most expensive part of the process.
They are. And what remains has to be handled by another mitigation technique, symbolization separation.
Right.
The goal, always, is to keep the overhead on the production machine at an absolute minimum. So the raw profiles and their metadata, the memory addresses, instruction pointers, event counts, they're saved immediately in their raw format and just shipped off the machine as fast as possible.
And the heavy lifting, the CPU-intensive process of symbolization.
Which is mapping those collected memory addresses back to human-readable source code function names.
That is performed entirely offline on a separate fleet of dedicated low-priority machines.
Precisely. That separation ensures that the production fleet never, ever pays the computational cost of interpreting the data it's generating.
Okay, so once all that raw sampled data is collected and offloaded, the next massive challenge begins.
Right.
Turning a raw memory address into a useful function name. And here's where it gets, I think, really interesting, because symbolization, as you mentioned, is complicated by just standard deployment practice.
The complexity is layered, for sure. Application binaries are typically deployed stripped of their debug and symbolic information.
And this is just standard practice, right? To save network bandwidth and disk space.
Absolutely standard. So the production machine only has the bare executable, which means the raw profile gives you an address like 0x4012.803, but no corresponding function name. It has no idea what that address means.
And you mentioned a couple of other wrinkles here. You have to deal with dynamically generated code and operating system components.
That's right. You have systems like Java virtual machines or virtualization tools like QEMU that dynamically generate code during runtime, code that never existed in a static binary file.
So there's nothing to look up.
Nothing to look up. And the system also needs to symbolize the core operating system kernels and the loadable modules, which require their own separate symbol maps.
So to handle all of this, GWP had to create some kind of external central source of truth for symbols?
Which is the binary repository.
The binary repository.
Correct. They store the unstripped binaries, these massive files containing all the necessary debug information, in a global repository. But just retrieving and processing symbols for a single day's worth of profiles is a monumental task.
Why is that?
The binaries themselves are huge, for one, and sequentially looking up symbols for every single sampled instruction, that would take weeks of computation time.
This is a classic scaling problem. It's just begging for a distributed solution.
It absolutely is. And that's what they did. To reduce the result latency and process those daily incoming gigabytes of profiles, GWP distributes the entire symbolization process across a few hundred machines using MapReduce.
Can you walk us through how that works?
Sure. The map step basically reads the raw profile samples and figures out which binary files and which offsets need to be symbolized. It creates a work list.
And the reduce step.
The reduce step then takes that work list, gathers the needed symbols from the global repository, and generates the finalized human-readable profile.
And this parallelization is what makes it possible to do daily.
It's what transforms a weeks-long sequential task into one that can be reliably completed every single day.
Okay, so once it's all symbolized and verified, the data needs a permanent home, a storage system that's optimized for analysis. How is the profile data structured for querying?
So first, for long-term archival, the raw performance logs and their corresponding binaries, which is the fundamental evidence, are archived using the Google file system, GFS. That ensures auditability and durability.
But that's not what users query against.
No. For operational use, for running real-time, ad hoc queries and automated analysis, the samples are loaded into a read-only dimensional database.
An OLA cube.
Essentially, yes. It's an OLA, or online analytical processing cube, that's distributed across hundreds of machines. And this structure is absolutely critical.
Why?
Because OLA databases are ideally suited for aggregating over enormous, sparse data sets using these cross-cutting filters, which is exactly what a GWP profile is.
Let's dive into the query structure itself then, because that really defines the utility of the whole system. A GWP profile record is stored as a tuple. Event, sample counter, M-dimension vector.
Yeah, the event part is simple. It's the type of measurement: CPU cycles, retired instructions, L1 or L2 cache misses, lock contention time. It has to be something numeric that you can add up.
And the sample counter is just the raw number of times that event occurred for that particular sample.
Right.
And then there's the M-dimension vector. This sounds like the engine that provides all the context.
It is the context engine. The M-dimension vector is all the tagging information, and there can be dozens of tags that defines everything about that sample.
Give me some examples.
It includes the application name, the specific function name, the hardware platform ID, the compiler version used to build the binary, the name of the executable image, the data center location, the kernel version, the specific build revision.
So without that rich tagging, the sample is just a meaningless number.
Completely. And the power comes when users query this database, because they're performing filtering and grouping across all of these M dimensions at the same time.
So a user could say something like, show me the top 10 functions.
Right. The top K functions, those are your grouping keys for CPU cycles on the search application running in Data Center X that was built with compiler version 12.0.
And those last bits are the filtering restrictions.
Exactly. You select K keys from the M dimensions to group by, while you filter by restrictions on the remaining MK dimensions. This dimensional structure is what allows for that rapid cross-cutting aggregation.
And I imagine these queries aren't always instantaneous.
They're not. Individual queries can sometimes involve scanning massive data partitions and can take tens of seconds to complete.
Yeah.
So to combat that, the profile server uses very aggressive caching to hide that latency for frequently requested aggregations.
Which makes the system feel responsive even though it's crunching a massive amount of data behind the scenes.
That's the idea.
We've now built this incredibly sophisticated system that collects, symbolizes, and stores sample data with minimal overhead. But the big fundamental question is still there. How do we trust it? How do we trust a number that's derived from a tiny, randomly selected subset of the entire data center?
The reliability problem.
Yeah. I mean, relying on heavy sampling introduces inherent statistical variation. So how do the GWP engineers mathematically ensure that the data is representative and sound, especially when the underlying data center workloads are constantly changing?
This is where the really elegant application of mathematical and information theory algorithms comes in. And it's a fascinating problem because you can't directly measure the true instantaneous performance of the whole data center.
Because the measurement process itself would change the result?
It would change the results. So you have to rely on indirect methods. Specifically, you have to focus on the stability of the profile over time.
And they use two core algorithms to establish this mathematical trust.
They do. The first is entropy, which they use as a measure of variation or flatness in a profile.
Entropy. Okay, this is a term from information theory.
That's right. We needed a kind of mathematical signature for profile stability. Entropy, which is written as $1 measures the uncertainty that's associated with the distribution of samples.
What's the formula look like?
The formula is 1 so log, where n is the total number of entries in the profile, so functions or routines, and delox just the fraction of total samples that are attributed to that specific entry, $60.
Okay, so let me see if I've got this. If all the activity is spread evenly across, say, 100 different functions, the profile is flat.
Right. That means it has high entropy. Lots of uncertainty about where the next sample will land.
And if 90% of the activity is concentrated in just one function, the profile has a hotspot.
Which means it has low entropy. You're pretty certain the next sample will land in that one hot function.
So the key insight here isn't the entropy value itself, but its stability over time.
That is it, exactly. If your sampling mechanism is consistently capturing the behavior of a stable application, then the entropy of the resulting daily profile should fall within a very tight, predictable interval.
And they validated this.
They did. By analyzing daily application-level profiles, they observed that the entropy was indeed remarkably stable between dates. That confirmed that the overall workload and system behavior were behaving predictably.
And then they took this analysis a step further by looking at the per-machine profiles, which have to be inherently more noisy.
Yes, and this is where the math revealed something really fascinating about the application's internal structure.
What did they find?
For per-machine profiles, they found that once you collect a certain minimum number of samples, the entropy does stabilize. But instead of settling on one single level, the entropy of the samples often clustered around two distinct levels.
Two levels.
Yeah. For one specific major web serving application, for example, they found profiles clustered either in an entropy range between 5.5 and 6, or in another range between 4.5 and 5.
What does that mean?
It clearly suggested that the application had two major distinct behavioral states, maybe an idle state and a heavy processing state. And GWP sampling was successfully distinguishing and consistently capturing both of those states, even with all the inherent statistical noise.
That's powerful validation, but as you mentioned, entropy has a blind spot. It ignores the specific entry names.
It does.
If function A and function B swap percentages, function A drops from 10% to 5%, and function B rises from 5% to 10%, the total entropy might stay exactly the same, but the performance profile has definitely changed.
That is precisely why they introduced the second core metric, the Manhattan distance, which is also known as the L-Belong distance.
And this one does look at the names.
It specifically measures the change based on the same entries between two different profiles.
The algorithm for this one tracks the difference in percentage consumption for the pop functions. It's MXY, 1K, PXY, PX.
Which is just the sum of the absolute percentage differences between the top K entries in profile X and profile Y.
So a smaller Manhattan distance means less variation. The profile didn't move as much from one day to the next.
Right, and analyzing this metric against other system data gave them some crucial insights into the very nature of system noise.
What did they learn?
They found that memory allocation profiles and thread contention profiles generally have smaller, less correlated Manhattan distances. That suggests their variation is mostly intrinsic to the application's own logic.
But CPU profiles were different.
Very different. CPU time profiles correlate very closely with hardware performance events, which means their variations are often extrinsic. They're caused by outside factors like shifting job priorities or sudden spikes in workload.
And the Manhattan distance also helped them provide a statistical rule for confidence based on sample size, which is just critical for trusting any kind of sampled data.
Absolutely vital. They mathematically cross-validated this. They compared a small subset profile against the complete, large profile derived from the same run.
And what was the relationship?
They established that the distance correlates roughly by a power trend line that approximates a classic square root relationship. Variance is approximately 2 tollers divided by the square root of no, where no knows is the number of samples.
So in simple terms, as you get more samples, the variation goes down predictably.
It proves that noise is reduced in a statistically sound way, simply by increasing the sample size. It gives you confidence in the data.
Okay, finally, let's look at how they cross-validate stability using derived metrics. This is about proving that even calculations based on combined samples remain consistent.
The best validation here is the derived cycles per instruction, or CPI.
Which you calculate by taking the HPM profile for cycles and dividing it by the HPM profile for retired instructions.
Correct.
And just to remind everyone, a lower CPI essentially means your processor is wasting less time waiting on memory or dealing with cache misses. It's the cleanest gauge of instruction execution efficiency.
Precisely. And what they found was that the drive CPI, when aggregated on a daily basis, was remarkably stable. For one application, it consistently fell into a tight interval, say between 1.7 to 480 I, across many different dates.
And that inherent stability proves that the underlying HPM data is sound.
It does. And furthermore, GWP's CPU cycles profile was cross-validated against the data center's much more coarse-grained monitoring system, which just tracks overall CPU utilization.
How did they connect those two?
They used a conversion formula: core seconds equals cycles times sampling rate times the sampling period, all divided by the average CPU frequency. And they found that the data aligned.
So they validated GWP's finer-grained reliability against trusted but much coarser monitoring systems.
That's right. It builds a case, layer by layer, that you can trust the numbers.
So with this continuous stream of reliable, mathematically validated data flowing, GWP transforms. It goes from being just a performance tool into a critical infrastructure optimization engine.
It really does.
And this starts with the ability to identify the hottest shared code.
This is where that fleet-scale intelligence truly pays off. If you only profile applications individually, you're just going to focus on the functions that consume, say, 10% of that application cycle.
They're stuck in your own little world.
You are. And that approach completely misses code that is used minimally, but by 1,000 different applications.
But when GWP aggregates that data across all applications,
routines that consume the most cycles overall, across the entire fleet, suddenly become obvious and get prioritized.
the source material gives a canonical example of this, which is just staggering in scale.
It is. The GWP profiles reveal that the widely used zlib compression library, a foundational, seemingly harmless component that's used in everything from file storage to network communications.
Yeah, it's everywhere.
It's everywhere, and it accounted for nearly 5% of all CPU cycles consumed across the entire global fleet.
5% of everything.
5% of everything.
Mhm.
This single finding motivated a massive, prioritized, multi-team optimization effort aimed solely at reducing the overhead of zlib.
That one discovery alone probably justifies the immense investment in the entire GWP infrastructure. And yet, no single application owner ever saw that routine as their primary bottleneck.
That's right. And this led to an entirely new internal metric, didn't it?
It did. Because GWP can accurately measure the percentage of total fleet cycles consumed by any function, they can directly translate a performance improvement into estimated annual financial savings.
Which gives rise to this popular informal metric, the dollar amount per performance change.
It provides direct economic justification for optimization projects that would otherwise seem minor to a single team.
It's a powerful motivator.
GWP is also vital for evaluating hardware features and configurations before you do a big, expensive rollout.
It's used continuously for early evaluation. For instance, if you want to assess the benefit of a new microarchitectural feature, like a specialized coprocessor for floating point computation.
You don't have to guess anymore.
No more guessing. GWP can look at the total percentage of floating point intensive computations across the entire fleet and give you a clear cost-benefit analysis before you purchase millions of dollars worth of hardware.
And it can also act as an auditor.
Yes, it helps auditors identify specific applications that are still running on older, less efficient hardware configurations that should be retired or migrated immediately.
Okay, now we get to the true algorithmic utilization of GWP data. This is where it gets really advanced. Optimizing for application affinity, using linear programming for job scheduling.
This addresses a fundamental reality of large data centers. Not all machines are created equal, and not all applications run equally well on all machines.
Right. An application might run 10% more efficiently, have a lower CPI on one generation of processor versus another because of subtle microarchitectural details like cache size or instruction pipeline differences.
And a human operator can't possibly track this manually across thousands of apps and dozens of hardware types.
But GWP can.
GWP continuously measures that CPI efficiency metric for every application and every platform combination. It builds a massive matrix of performance data.
And they then use that massive matrix of CPI values to dramatically improve job scheduling. So how is this optimization formulated mathematically?
It's formulated as a classic linear programming problem. The goal is to find the optimal assignment of workload to hardware,
And the unknown variable they're solving for is low dollar.
which represents the instruction samples, or you can think of it as the workload fraction of application J that should be assigned to run on platform I.
And the objective of the whole thing is the economic goal. Minimize the total cycles consumed across the entire fleet.
That's right, the solver aims to minimize the sum of CPIJ times load A. And this is subjected to two non-negotiable constraints to make sure the system actually stays operational.
Okay, constraint number one is about demand.
Right. The total instruction load required for any given application has to be fully met, regardless of which machine type it ends up running on. The sum of load A equals the total load A.
And constraint number two is about capacity.
The total cycles consumed on any given platform must not exceed its physical capacity. The sum of CPIJ times load A has to be less than or equal to the capacity.
And they measure that capacity based on the total cycle samples available for that platform.
They do. They use a sophisticated simulated annealing solver to tackle this massive optimization space.
Yeah.
And the result of applying this mathematical approach is really the headline finding of this whole system, isn't it?
It seems like it. What was it?
It is the ultimate validation of the GWP philosophy. Even after application developers had manually mapped their most critical applications to what they perceived were the best platforms.
So after the human experts did their best.
This algorithmic, mathematically rigorous approach consistently measured a 10 to 15% potential improvement in fleet-wide efficiency, in most cases where you have multiple jobs running across multiple platforms.
That gap, 10 to 15%, that's the measurable difference between human intuition and continuous data-driven optimization.
That's what it is. It's a huge number at this scale.
Moving on, another powerful application is feedback-directed optimization, or FDO, for compiler improvements.
Yes, FTO systems rely heavily on runtime profiles to guide the compiler on how to aggressively optimize code, things like function inlining or code layout.
And GWP provides the perfect input for that.
The perfect input. It's profile data derived from live production traffic. This is inherently higher quality and far more representative of real-world usage than any profile you could get from test inputs or simulated benchmarks.
So GWP extracts this sampled profile data and just feeds it back to the compiler.
Exactly. And crucially, they found that even an aged profile, say data that's a month old, can still significantly improve the performance of a freshly released binary.
As long as the core logic hasn't totally changed.
As long as developers haven't radically altered the application's critical program sections, yes. And given the extremely rapid release cycles of modern web companies, this is an infrastructure optimization advantage that is hard to overstate.
And finally, GWP provides these invaluable capabilities for monitoring and auditing infrastructure changes. It acts as the mathematical conscience of the system.
That's a great way to put it. By allowing that flexible grouping of profiles by keys like compiler version or a specific data center or platform rollout date, they gain these powerful auditing abilities.
So if a new compiler version is rolled out,
GWP can instantly measure how quickly that transition is actually happening across the fleet. Or if an unexpected performance drop occurs, say an increase in CPI or L2 cache misses, a sudden change in the hot functions in the daily profiles can trigger a fine-grained comparison that points the blame directly to a source code revision, a new kernel version, or a specific data center rollout.
this ability to monitor and attribute change mathematically, fleet-wide,
Yeah,
it's absolutely invaluable for maintaining system stability at hyperscale.
it is.
So what does this all mean at the end of the day? We've seen how Google-wide profiling takes these minimal resources, an astonishingly low overhead of less than 0.01%,
It's still hard to believe.
but it yields these maximal aggregated insights by leveraging distributed collections and very sophisticated mathematics. It fundamentally moves performance analysis from a reactive single-machine debugging activity.
A proactive fleet-wide intelligence operation.
Yep.
And the core innovations that really make this possible are, I think, threefold. First, it's that two-dimensional sampling strategy. That's the key to being non-intrusive.
Right.
Second, it's the architecture. Leveraging MapReduce for scaling complex processes like symbolization and the dimensional database, the OLAP cube, for querying.
And third,
It's the application of those informational theory algorithms, entropy and Manhattan distance, to mathematically validate that sparse, noisy profile data. That's what transforms data center operation from guesswork to mathematical certainty.
and we know the GWP system is always evolving. Future directions include integrating GWP profiles with other performance data sources and applying advanced data mining and machine learning techniques to automatically detect those interesting subtle patterns in profiles without even needing a human to query them first.
And if this infrastructure can optimize millions of dollars in computation annually, it raises a powerful question about the limits of data-driven optimization. The provocative thought for you to mull or explore on your own is this. If performance data from every distributed system, and I mean large-scale scientific simulations, global financial networks, you name it, were continuously measured and validated with GWP's level of mathematical rigor, what new scientific or social problems of a global scale, problems that require massive computation, could be solved or optimized that we currently consider just too complex or too costly to even touch?